Hello everyone, welcome back to our engineering mechanics dynamics class. Today this is our lecture 20. We're going to talk about principle of angular impulse and momentum. This will be our last session for chapter 15, and from next lecture we'll start chapter 16. One of the example of angular momentum, if you see this image here, the park, this rotating ride has angular momentum because it's rotating about this point in a circle. So you can apply angular impulse and momentum theory on those if needed. So let's see what is our learning objective is. So today's learning objective is formulate the principle of angular impulse and momentum. So we'll formulate the formula for angular impulse and momentum. And again, some example is this ride of the park. You see the people, the persons are rotating. So this ride is rotating in this direction, and then people are tends to go outward. So they have angular motion around this axis. So we can apply the principle of angular impulse and momentum on this scenario. Also here, if a car moves along this path, and this is almost a circle, so for example about any point here you can have angular momentum taken. So this is the scenario we can apply this. So let's formulate our principle. CIPLE, principle of angular impulse, impulse and momentum. So remember, we also had a principle of impulse and momentum, and this is just only change is that we're gonna do it for angular scenario. So we have to start with the definition. So in a previous lecture we saw the summation of all the moment is equals to angular momentum, first derivative of that, which is d over dt of the angular momentum h dot. So if we take another step and we say if we take a integration from time t1 to t2, so if we take integration and we just take the dt on the other side and we keep h on the other side, dh dot. So if we take and also integration on this side, so if we do the integration, we will be getting integration from time t1 to t2 m naught dt, and integration of dh will be h2. If we do the integration, it will have from t2 to t1. So for time t2, if our angular momentum is h02 and minus the h01, and you know where we get it from. If you take the derivative of integration of dh, right, which gives you h over so t2 t1, so you will get the t2 t1 from here. If we plug the value, if for time t2 if your angular momentum is h02 minus for t1 is h01, so which gives us, if we further simplify and take this term on the other side and this term on the other side and keep this term on this side, so we'll have h0 prime 1 plus the change in integration of momentum equals to our HO for 2, and this equation is called our principle of angular impulse and momentum. So let's again talk about what are the terms is. The H01 and H02, or HO1 and HO2, are the moment of the linear momentum of the particle with respect to a point O. This is HO. So from point O, these are the linear momentum, and these H are defined as from previous lecture, position vector cross product with mass and vector velocity vector. So these are the H definition. Now we left with another term, that is this term here. Remember when we talk about impulse, it was the summation of forces, integration of time. So now we have summation of moment and with time. So this is called the angular impulse. Angular impulse. So this is our angular impulse, and this M is defined as M naught, that we know from previous lecture, cross product with force. So this is our principle of angular impulse and momentum. So angular impulse can be written as T2 from T1 M naught dt, and if we plug the definition of M naught, we can still write R into F dt. So this is our angular impulse. If we apply the same formula for system of particles, because this is for only one particle, if we do for system of particles, and all the steps of cancelling the internal force, we can write the same principle of angular impulse and momentum for system of particles as summation of H naught 1 plus summation of T2 T1 momentum with respect to position O, point O, equals to the summation of H naught HO, so angular momentum with respect to O and after time T2, and this is for system of particles. System of particles. Okay, so now see in a vector form how our equation the principle of impulse and momentum looks like. So in our chapter 15 at the beginning, when we're defining what is impulse is, just impulse, not angular impulse, for just impulse, we talked about having the equation, if you remember, mass into velocity 1 plus summation of T2 over T1, and we had the F force dt, which is equals to M, the final momentum. This was for the first equation that we derived. This velocity is in vector, this velocity also vector, so this is vector form. And here in this chapter we just derived is angular momentum. So instead of a linear momentum, now we have an angular momentum. This is the second equation. They are not related, but this can be applied in a single problem. So instead of a just impulse, we will have same from T1 to T2. We will have angular momentum dt, and we will have, instead of a linear momentum, we will have angular momentum, which is 2 for time 2 t2 with respect to origin or any point O. So this is the first equation, this is our second equation, and these are the vector form our principle of angular impulse. So now let's talk about how can we define this equation in scalar formation or scalar form. So in scalar formation, we can write this equation as in x coordinate, velocity is a vector, so it will have an x component plus summation of all the force t2 t1 fx dx equals to mvx2. So this is in x direction, and the second equation will be m vy1 plus summation of t2 t1 fy dy, dt actually, because it's time with respect to time t, and this is also would be dt not dx, equals to our m vy2, and we will not have a z term here, because remember this equation that we are forming is only about for particle motion in which is confined to move only xy plane. So we're considering that the particle moves only on xy plane or any plane here in xy. If it's xy, then we can write these two equations, and we'll have our angular momentum equation as h01 plus t2 over t1 moment dt and h02. So this is for a particle in scalar formation without any vector direction for a particle that is moving on a xy plane. So we have our last thing that we have to talk about is conservation of angular momentum. Conservation of angular momentum. So when we talk about conservation of angular momentum, let's go back to our equation that the initial angular momentum plus the angular impulse t2 from t1 m0 summation of dt equals to h02. So if we assume that there is no angular impulse, which is 0, then the conservation theory tells us h01 equals to h02. So we also had a conservation of momentum equation, and now we're having conservation of angular momentum equation. Then this is from time t1 to time t2. So just to remember that we can apply the conservation of momentum and conservation of angular momentum at the same time, but there is one interesting thing to notice is that if we have a scenario when the particle, for example, is moving along a curved path, and there is the resultant force acting exactly towards the origin. So the forces are acting exactly towards the origin, right? So in this case, the impulse is not 0 because there is a force acting F. So the summation of force F dt is impulse, which is not 0, but the angular momentum, which is which is the multiplication of R cross product F, right? So in this case, the R would be the same direction as the force is acting. So the force is towards the origin, F, and the R is also in the same direction. So the angle would be 0. And only in this case, the angular impulse would be 0. So this is the interesting thing. Though even the force is acting on a particle here, at the same time when the impulse is not 0, because it's just the force and with time, but the angular impulse can be 0. It's funny and interesting. So and then so it also implies that when the force is acting, the conservation of momentum may not be valid because there is impulse, but at the same time the conservation of angular momentum may be valid because the angular impulse is 0, and that implies summation of angular momentum before time t1 and after time t2 could be 0, could be conserved, though there was a force acting, but it was acting along the direction of the point where you're taking the moment. So that was it for today. We'll be solving problems and we'll be moved to our next chapter, chapter 16. See you in next lecture. Thank you.